think an engine gets banned because it's unreliable or unsafe, right? But after digging through decades of manuals, case studies, and user reports, I found one that was banned for the exact opposite reason. It was simply too tough to kill. And that paradox led me straight to the Deutz F4L912, an air-cooled workhorse so durable that regulators had no choice but to shut it down. When you look back at the Deutz F4L912, you're not just talking about an engine. You're looking at a product of wartime necessity. Its roots go all the way back to World War II, when German engineers faced a nightmare scenario. The problem? Traditional water-cooled engines just couldn't cope. In the freezing Russian winters, coolant would solidify into useless blocks of ice. In the North African deserts, radiators boiled over like kettles. And in combat zones, one stray bullet could turn a cooling system into a ticking time bomb. Something had to change. That's when Deutz, then known as Klockner Humboldt Deutz, came up with a radical idea in 1944. Forget water altogether. Instead, they designed an air-cooled diesel engine. This wasn't just clever engineering. It was survival thinking. If you could eliminate the weaknesses of coolant systems, you'd have an engine that could run in the Arctic, in the Sahara, or in the middle of a battlefield. No radiators to puncture, no pumps to seize, no antifreeze to freeze or boil, just pure mechanical muscle cooled by nothing more than air rushing across fins. Now, meet the F4L912. On paper, it doesn't sound like a monster. A 4-cylinder naturally aspirated diesel with 4.31 liters of displacement. It pushed out 72 horsepower at 2,500 RPM and made 247 Newton-meters of torque at just 1,450 RPM. But the beauty of this engine wasn't the numbers, it was the way it was built. Each cylinder had its own detachable aluminum head, bolted onto a solid cast-iron crankcase. That meant, if one cylinder had issues, you didn't need to tear the whole engine apart, just fix the bad one. The pistons ran with 3 precision rings in carefully machined bores, and the whole setup was kept cool by an axial flow blower, pushing air over those distinctive finned surfaces. But how could such a simple, almost primitive cooling method keep a diesel engine alive in deserts, jungles, and even frozen battlefields when far more advanced systems often failed? You see, the Deutz F4L912 was clever. Take its cooling system, for example. Instead of relying on fragile radiators or complicated electronics, it used nothing more than air, precision, and smart design. A belt-driven fan pulled air through a shroud, first pushing it over the oil cooler, and then across the finned cylinders and heads. That meant the whole engine stayed at just the right temperature without fancy sensors or electronics. It was mechanical purity at its best. If the fan spun, the engine stayed cool. Even the fuel system was beautifully simple. It used a purely mechanical P-type injection pump, carefully timed with port and helix control. Each cylinder got its own dedicated fuel line leading to direct injection nozzles. No electronics, no fragile wiring, nothing extra to fail. Once the engine was started, it didn't really care if you had electricity or not. It would keep on running. In an era where electrical failures could bring a machine to its knees, this made the Deutz nearly bulletproof. By the 1970s, 80s, and 90s, this engine had become a legend in the industrial world. You could find it everywhere, on construction sites, powering irrigation pumps in farms, running compressors, driving generators, or tucked inside heavy agricultural machinery. Its appeal was simple. It didn't break down easily, it didn't need much maintenance, and it didn't stop working just because the environment was tough. Construction crews loved it because dust and debris that clogged water-cooled engines didn't bother the F4L912. Farmers trusted it because it didn't freeze in winter or boil in summer. It was the kind of engine you could run hard day after day, and it would just shrug it off. Now here's the twist in the F4L912 story. The very design that made it nearly unkillable also turned out to be its biggest weakness. You see, air cooling sounds great on paper. No radiators, no pumps, no coolant. But when you put it in the real world, on farms, dusty construction sites, or in factories, the system started to show cracks. The fan was belt-driven, constantly forcing air over those big cooling fins. But dust, straw, and debris loved sticking to the fan blades. Over time, this gunk built up, throwing the fan off balance. That imbalance caused vibrations, and those vibrations didn't just make noise. They could slowly chew away at crankshafts and other critical parts. And it wasn't just the fan. The fins themselves were like dirt magnets. Oil mist, grime, and even bugs would cake onto them. Once the fins got coated, they couldn't shed heat as efficiently. Unlike a radiator that you could flush or pressure wash, these fins were exposed and hard to clean thoroughly. As efficiency dropped, the engine started running hotter than intended, putting stress on almost every moving part. That heat wasn't uniform either. Since each cylinder had its own head and cooling path, some parts of the engine would be hotter than others. Engineers call this a thermal gradient, basically, uneven heating across the engine, and that's a big deal. Different temperatures meant parts were expanding and contracting at different rates, which slowly fatigued pistons, heads, and connecting rods. But here's the real deal breaker: emissions. As the world tightened diesel regulations, new after-treatment systems like DPFS, SCRS, and DOCS became mandatory. These systems need precise thermal control and electronic management to work properly. The F4L912, with its purely mechanical air cooling setup, just couldn't play in that league. It was too old school, too simple, too incompatible with modern emissions gear. So while the engine could survive the battlefield, the farm, and the job site, it couldn't survive the clean air laws of the modern world. Its toughness was legendary, but its simplicity left no room for evolution. And that's what ultimately sealed its fate. But how does an engine so reliable that it could outlast the machines it powered end up banned worldwide? The answer isn't about what it couldn't do mechanically, but what it couldn't hide on paper. If there was a true nail in the coffin for the Deutz F4L912, it wasn't a mechanical failure, it was emissions laws. Starting in the late 2000s, governments rolled out new regulations that made life tough for every diesel engine. By the time Tier 4 final and EU Stage 5 rules came into effect around 2019, the bar was set so high that the old-school Deutz didn't stand a chance. The new limits were brutal. Engines had to keep particulate emissions under 0.02 grams per kilowatt hour. Basically, you weren't allowed to see smoke anymore. On top of that, nitrogen oxide had to stay under 0.4 grams per kilowatt hour. To hit those numbers, you needed surgical precision in combustion, backed by exhaust cleaning systems. That's something a purely mechanical, air-cooled diesel just couldn't deliver. Modern diesels started relying on a whole lineup of emissions tech. You had EGR systems to recycle exhaust gas, DPF filters to trap soot, SCR systems with urea injection to cut down NOx, and oxidation catalysts to clean up the leftovers. But here's the thing, these systems don't just bolt on. They need electronics to monitor temperatures, sensors to adjust fuel injection, and a cooling setup to keep everything in the right operating window. The F4L912 had none of that, nor the space or thermal control to support it. In fact, its biggest strength, those naturally high running temperatures, became its undoing. With air cooling, you couldn't fine-tune the heat the way water-cooled engines could. That made it nearly impossible to run the delicate after-treatment hardware modern laws demanded. The engine's simplicity, once its greatest selling point, turned into a hard stop. So, one by one, countries began shutting the door. Europe, the US, Canada, and anywhere with strict emissions laws banned the sale of new equipment powered by the F4L912. Old ones were still allowed to run, and many of them still do today, but no new units could legally roll off the production line. By 2020, the end was official. Deutz Australia announced it was pulling the plug on several of its iconic air-cooled engines, including the F3L912 and F5L912. The F4L912 managed to hang on a little longer in a few markets, but the message was clear: its days were numbered. Deutz was moving its focus toward water-cooled engines that could meet modern emissions standards without a fight. The company tried to put it politely. Official statements described the F4L912 as best suited for markets without emission regulation. In other words, if you lived somewhere with strict pollution laws, the F4L912 wasn't welcome anymore. Technical bulletins even hinted at the engine's vulnerabilities, warning about cooling system sensitivity and suggesting certain operating environments to avoid. For an engine once celebrated as indestructible, it was a quiet admission that the design had reached its limit. To soften the blow, Deutz promised to keep genuine parts available for about 10 more years after production ended. But the truth was unavoidable. No new F4L912 engines would roll off the line for regulated markets. After half a century of powering farms, factories, and construction sites, the legend was being retired. So why did air cooling fail in the long run? The answer lies in physics. Air simply doesn't carry heat away as efficiently as liquid coolant. That meant the F4L912 always ran hotter than water-cooled engines. Ironically, this trait once worked in its favor, giving it great fuel efficiency and durability. But when emissions rules demanded razor-sharp temperature control, it became a liability. Modern diesel aftertreatment systems like DPFS and SCRS live or die by precision. ADPF needs exhaust temps above 600 degrees Celsius for regeneration, while SCR systems require exact urea injection timing based on both heat and flow. These systems rely on sensors, actuators, and electronics to constantly adjust conditions. The F4L912, with its simple mechanical injection and air cooling, just couldn't deliver that level of accuracy. The F4L912's design, once its biggest strength, eventually became its downfall in the emissions era. Back in the day, its modular layout was genius. You could service one cylinder without tearing the whole engine apart. But as emissions rules tightened, that same design created a nightmare. Each cylinder had its own head and cooling path, which meant combustion temperatures were never perfectly even. Modern engines need uniform combustion across all cylinders to keep emissions clean and consistent. The F4L912 simply couldn't deliver that level of balance. Space was another deal breaker. New aftertreatment systems like DPFS, SCRS, and DOCS take up a lot of room. They need bulky filters, catalysts, and a web of plumbing to work properly. The compact air-cooled architecture of the F4L912 left no extra space to bolt any of this on. It was a beautifully simple design, but it left no room for growth. Compare that to today's Deutz engines, the TCD water-cooled series. These are the polar opposite of the old F4L912. They're loaded with tech: common rail injection, electronically controlled EGR, turbocharging with intercoolers, and full emission systems integrated right in. A TCD 4.1 L4, for example, squeezes out 154 horsepower from roughly the same displacement as the F4L912. On paper, that's impressive, but it comes at a price: complexity. These modern engines need ECUs, dozens of sensors, after-treatment systems, and precise thermal management to keep everything working. And here's the thing: reliability doesn't mean the same thing anymore. The F4L912 could run for decades with little more than oil and filter changes. What used to be a field repairable workhorse is now a machine that often requires dealer tools and specialized training just to troubleshoot. That shift hit industries hard. Manufacturers had to redesign equipment to fit larger, more complex power plants. Operators saw costs rise with DEF consumption, DPF maintenance, and electronic servicing. And for remote areas or developing markets, the economics often didn't make sense. The old Deutz could run in the middle of nowhere with basic tools. The new ones? not without a laptop, a technician, and a lot more money. You see, the end of the F4L912 is more complicated than just it polluted too much. In fact, it exposes a fascinating environmental paradox. Sure, its emissions were higher than today's strict standards, but here's the catch. One F4L912 could run for decades, often outlasting multiple generations of modern engines. When you factor in the energy and resources needed to build those replacements, the green picture starts to look a little blurry. Was replacing one long-lived workhorse with several shorter-lived engines really better for the planet? That's the uncomfortable question the F4L912 leaves behind. Its mechanical simplicity made it even more eco-friendly in its own way. You could rebuild cylinder heads, overhaul pistons, and keep the same engine alive with basic tools. By contrast, many modern diesels, stuffed with electronics and after-treatment hardware, become uneconomical to fix once a major failure hits. Instead of rebuilding, people scrap and replace them, which ironically creates more waste. Air-cooled engines also filled niches that water-cooled designs still struggle with: extreme climates, remote locations, or industries where downtime simply wasn't an option. Losing the F4L912 meant losing an engine that could run in places where modern machines are far more fragile. Modern engines are marvels of electronics and integration, squeezing more power out of less fuel while meeting regulations. But in the process, something was lost. The old-school mindset that prioritized repairability and raw toughness above all else. Regulations didn't just kill the F4L912, they erased an entire design philosophy. Today, the F4L912 lives on only in legacy machines or regions without tight emissions laws. Production for major markets is gone, closing the book on a lineage that began in World War II and became an industrial icon. Its death wasn't just the end of a model, it was the end of an era where mechanical elegance was enough. The irony? Many F4L912s are still running, and they'll probably keep running for decades. While newer engines may be cleaner on paper, they'll likely come and go while this banned dinosaur just keeps chugging along. Proof that sometimes being too tough really is a problem. What do you think? Should indestructible engines like the Deutz F4L912 have been banned, or should toughness always win over regulations? Drop your take in the comments below. And hey, if you secretly wish engines lasted forever, smash that subscribe button. It's the easiest way to keep these legends alive on your feed. When you're done, you've got two roads to take. Check out our deep dive on why the Detroit Diesel 8 V53 was banned, or let YouTube surprise you with something it thinks you'll love.